So now let's talk about some types of forces. The normal force is a big one. It is a perpendicular contact force exerted by one surface on another. So anything that is touching has a normal force. Okay. If this isn't a very good straight line. Let me draw a better one. So if this is our object, let me draw like a square or something. If this is our object, we have a normal force of the table acting on the object, and that would be a normal force. So, and the normal force is always exerted up or perpendicular to the object. So if you have something at an angle, and then this will be our thing. Okay, the normal force is perpendicular to this surface, so it's going to go this way. So it's not always up, it's always perpendicular to the surface. So that's pretty key about the normal force. The next really important force is the drag force. And the drag force is a force exerted by a fluid. Now, we'll learn later that a fluid is not only a liquid. A fluid is a liquid. A fluid is a liquid. And a gas. So most of the time we'll talk about drag in a gas or drag in air, but you could also talk about like drag while you're swimming in the pool or something like that, or in the ocean. The drag force is always opposite motion. Sometimes people call it like air friction or water friction because you'll see that friction is also always opposite motion. The faster you move, the greater the drag force, and the larger you are, the greater the drag force. So if we have an airplane, okay, this is going to have a lot larger drag force than like a bug or something because this airplane is much bigger and it's also moving much faster. If you think about swimming in the water, when you look under the microscope, if you guys have ever done that, you see those little critters and they're zooming around really fast in the water. We don't do that. We actually, it's harder for us to move through the water because we're much bigger, and so we have a larger drag force. Terminal velocity is something we kind of think about when we're thinking about drag, and it is a constant velocity that occurs when the drag force equals the force of gravity. So if you have, they do talks about like a penny falling from a building, and they say, you know, when it hits the earth, it's going to like smash through the water or smash through the sidewalk or like go through someone's head or something. And what you'll find is that actually doesn't happen because eventually this drag force, which is always opposite motion, is going to equal the gravitational force. And your penny or whatever it is that's falling is going to reach that terminal velocity, and it's not going to get any faster than that. So things that are very light with a high surface area reach their terminal velocity faster, and heavy objects with a low surface area take longer to reach terminal velocity. So if you had like a bowling ball, that's not a good one. If you had a really dense little marble, or like a regular or a bowling ball that is as heavy as a feather or a marble, that little tiny heavy bowling ball, that little tiny heavy marble will reach their terminal velocity faster than that really big light bowling ball, because that bowling ball is heavier and the marble is light. Now, these two forces are really, really important. Friction, we will talk about friction a lot, and it is always opposite motion. So you can see this ice skater, he's pushing his skates, he's moving towards us, and the friction is moving past is moving into the screen. And so if we were to draw it, he's moving this way, and the way he's got his skates caused the friction to be larger than the motion, which allows him to stop. If you have an air hockey table, you're not going to have a lot of friction. That's what allows those that puck to kind of slide around. If you guys have ever been to like one of those places that has an air hockey table where you have to put quarters in to play it, I remember when I was a kid, we would like kind of hold the puck and not let it go in the little thing because it only allowed so many goals or whatever. So we would hold the puck and we wouldn't let it go in, or like the last time we wouldn't let it go in, and then we would play without the air, and it wasn't nearly as fun. The puck would go like halfway across and stop rather than going back and forth because it had that friction of sliding on that table. A lot of people don't like friction. Friction is what causes cars to be inefficient and most machines to be inefficient. But if you think about friction, a lot of the things that we want to do, we could never do without friction. You could never walk without friction. If you think about like when it's raining and you have those shoes that don't have, that are like really smooth on the bottom, you just slip and slide everywhere. If there was no, that's what it would be like all the time. And so friction allows you to get a better grip on the surface. A car couldn't stop or it couldn't start without friction. Those tires turning on that rough road, that's what causes it to go forward when you're stopped, and that also what causes it to slow when you want to slow down. If there was no friction, you would just, if you think about like a car on a skating rink or something, it would just, you wouldn't have any control over it. Even this match, okay, there's that rough surface right here, and you scrape that match along that rough surface and it causes it to light. Without friction, you couldn't do that. So you couldn't sit in your seat without friction. So there's a lot of things that are actually really important because of friction. Static friction is the friction of not moving. When we get to our formulas, you'll see that you have to overcome the static friction. You have to make a friction that is more than your static friction in order to allow something to move. And your kinetic friction is the friction of moving. So the way you remember these, static actually means not moving, and kinetic means moving. A lot of times in college, football players will study kinesiology, which is the science of moving. The tension force is a specific name that we give to a force that is exerted by a string or a rope. When we do formulas and stuff, we go ahead and we assume that all strings and ropes are massless. And usually their mass is so light compared to anything else that we have that we're talking about that their mass is inconsequential anyway. When something is hanging, the tension of the rope is the weight of all the objects hanging from it. So right now, we have a tension force of this one bucket. But if we were to attach another bucket over here and another bucket over here and then a bucket to that bucket, okay, all of that, the tension force would increase, and it would be the mass of everything that's hanging from it. If we put rocks in here, that'll cause the tension force to be even higher, and eventually we'll get to the point where there's so much mass hanging from this rope that the rope will split and break. And we'll do an example problem in a little bit, kind of like that.